Okay, I want to explain this really important concept of quantum flux density and help you understand it, because it's really the measurement of light that is the best, the most appropriate, and probably the most commonly used with respect to measuring light for plants, for photosynthetic lighting. The first thing that I want to review real quickly, because it kind of confuses people and it'll be important in defining this issue of quantum flux density, is this idea that light behaves as both a wave and a particle. So, and again, you'll read more about this in the learning unit, but light behaves as a wave, and we can have light of different wavelengths. The wavelength is the distance between, say, two crests in that wave. The smaller the crest, the narrower, in other words, a shorter number or a smaller number, the higher the energy of that wave. So, and I'm just making these numbers up for descriptive purpose, but let's say then the distance from here to here is 450 nanometers, for example. This one is maybe 660 nanometers, for example. Now, we therefore can define the quality of the light based on its wavelength, and you see that throughout your notes. Within the visible spectrum, our eyes perceive these different wavelengths also as different colors. Red, blue, green, different colors of light. So a certain wavelength also corresponds, as you see in your notes, to different colors. So in its wave form, or when we're talking about light as a wave, we can describe the quality of that light as either by its wavelength in nanometers or by the color that our eyes perceive that as, if it's, again, visible spectrum light. Light also, however, just to make things very confusing, light's really rather amazing. It also behaves, in addition to behaving like a wave, it behaves like discrete particles. And these particles are commonly called photons, or they may be called quanta. Quanta being plural. Quanta or photons. And each of these particles, correspondingly, they have different energy levels. So each of these will carry a different energy level. And the energy level of, say, this photon, it would actually correspond back to some particularly energy level described as a wave. In other words, some photons have higher energy levels than other photons. Just like we talked about, the narrower the wavelength, the higher the energy. So they would actually correspond, we could correspond them back to certain wavelengths when we're describing it as a wave instead of a particle. But quantum flux density is going to look at light as a particle. And again, all these different particles of light or photons being given off will have different energy levels. And just as with the waves, our eyes would perceive those photons with different energy levels as being different colors. Or again, we can relate those energy levels back to their corresponding wavelengths. So, quantum flux density, which is also sometimes referred to, and I think I make this note for you, you might see it also called photosynthetic photon flux density, or PPFD. It's all the same thing. Quantum flux density, photosynthetic photon flux density, PPFD, they're all saying the same thing. And if we look at quantum flux density, you know, when I'm doing videos, sometimes I misspell, and I'm like, oh my gosh, did I just misspell this on a video here? Quantum flux density. Quantum is referring to the particles. Flux is time, and density is area. So when we look at the units of measure for quantum flux density, it's typically micromoles Remember that a mole is Avogadro's number, 6.02 times 10 to the 23rd. It's a huge number. So you'll often see quantum flux density reported as micromoles, just so we're not dealing with such a tiny, tiny little number. So it's just a millionth of a mole. A micromole, and that relates to the number of particles, or gets back to the idea of mole particles. Micromole per second, there's the time, per square meter per area. So we're really measuring the number of particles, light particles, striking a square meter every second. So it's sort of a single second measurement. Now there's one other caveat put on this quantum flux density measurement. And as you've seen in your notes, only light that falls within the 400 to 700 nanometer range, which is referred to as PAR, or photosynthetically active radiation, can really be used to drive photosynthesis. So when we measure these photons, we only want to measure photons that have an energy level that would also correspond back to sort of that wavelength. So the sensors we use to measure quantum flux density are designed to only be able to measure photons that have an energy level that would put them within 400 to 700 nanometers, and it ignores all the other photons. So it's really measuring the number of photons striking every second, every square meter per second, that have the appropriate energy level that they can drive photosynthesis. So let's look at one of my favorite little demos here. And it's my favorite because I think it helps understand some things. And also because I get to eat the M&Ms after I do this demonstration. So let's just pretend this is a square meter here, my little area. These are little photons or packets of energy, and you can see there's different colors because they're carrying different energy levels. And let's say only the green, the yellow, the reds, and the blues have energy levels that fall within the corresponding 400 to 700, or have energy levels that would also have them fall within that 400 to 700 nanometer range if we were looking at them as waves. The sensor on a quantum flux density meter will ignore those that don't fall in that range. So it's simply not going to see these brown ones because they don't have the right energy level. They can't drive photosynthesis. But it will measure these. So it's looking at a certain area over 1 second period of time, how many of the photons within that appropriate 400 to 700 nanometer range are striking that surface. Again, measuring it as particles. And that's essentially what quantum flux density is, or again, sometimes called photosynthetic photon flux density, or PPFD. So it's a particle measure in this case, measuring the number of photons that can drive photosynthesis that's striking that 1 square meter area every second. And that's the best measurement for measuring photosynthetic lighting for plants. Now later when you get going a little bit into your notes, you're also going to see something called DLI, or daily light integral. Daily light integral is basically the same thing as quantum flux density, except we're measuring the total number of photons. Instead of per second, it's how many photons struck this area over 24 hours, the accumulation, in other words. If we took these measurements every second and added it up over 24 hours, what does the 24-hour total end up being? And in those cases, because even though we're measuring quantum flux densities in micromoles, because we're not getting that many striking every second, over a whole day, that number goes way, way up. And you'll often then see daily light integral expressed as moles per 24 hours. But daily light integral is a number that's derived by measuring the quantum flux density. So hopefully that helps you a little bit to understand quantum flux density. Before I let you go, though, this is also a great way to understand, we were talking earlier about light quality and light quantity. I almost did you a video on this. Let's say here's all these little photons, right? Well, there's a certain quantity sitting here. And I may ignore that they're different colors and just measure the number, And that's a quantity measurement. But then I might start looking and saying, well, how many blues, how many reds, how many browns? That then is where we bring in that issue of being interested in light quality. And of course, as you can see, they are completely linked. And I mentioned in an earlier video, it's hard to separate them. If we think to that quantum flux density measurement, and we're both measuring total numbers of particles, but we sort of put that box around that measurement and said, but we're going to measure the total number of particles, but only within that 400 to 700 nanometer range. We're actually basically controlling for both light quantity and quality in that measurement. So anyway, hopefully that will help you a little bit if you read the notes and study up on that in this video. If you still come away on some of this lighting stuff a little bit confused, let me know. I've got some other demos, or we could chat, because light is a little bit of a sort of an odd concept, but at the same time, it's very, very important for us to understand.